Hello everyone, I hope you are doing a good job during this hard period, and I have been staying at home for nearly 2 months. I'm also looking forward to going outside, but during this hard period, the pandemic in Montreal is really severe right now, so I think staying at home and work at home is a good solution to this hard time, and I hope the pandemic will pass away soon. Today I will have this paper to share, Multi-Engine Reinforcement Learning for Network System Control. It is a conference paper published at ICLR 2020, and I think it is a very application-oriented research paper that is very related to my own research. So I'd like to share this paper with you. As usual, the presentation will be divided into two parts. The first is the motivation and the other is methodology. Now let's come to the motivation. The theme of this paper is, of course, multi-engine reinforcement learning, and it has a specific application, that is, it is designed for network system. On a network system, it has a very basic idea that it can achieve spatial-temporal Markov decision process. I think this method can also apply in any other multi-engine case, but network system is the most suitable for this paper. And the highlight of this paper is the spatial consideration and the communication scheme designed by the authors. And I think the highlight is rooted in their idea. So the core of this paper is the spatial temporal Markov decision process. Naturally, the solution to multi-engine reinforcement learning can be divided into two categories. The first is the multi-engine reinforcement learning that is without communication, and I think the classic and up-to-date research is the MADDPG, the multi-engine deterministic deterministic process gradient, and karma. And the similar framework of this research is that they have shared parameters. They usually share parameters to boost the training among each engine. So in this way, each engine can learn in the environment and share their experience efficiently. And the most common framework is the central critic and decentral actors. That is, the engine will execute based on their own local observation, but there is a unified critic to evaluate their performance. And the other solution is that it is based on the communication, and there are three basic ways to achieve the communication scheme. The first is the direct information sharing. In this work, the engines will transform the low dimensional policy feature to achieve the communication. And the second is the learnable communication protocol. In this research, the engine also will transfer the signal, but the signal can be learned during training. And the last is the attention based. It is focused on selecting which engines to communicate. And then let's come to the methodology. The spatial temporal reinforcement learning is the theme of this paper. For example, look at these intersections. This traffic network with multiple intersections, and we can regard each intersection as an engine, and each engine will learn a policy to control the traffic signal to make the traffic flow of this road network as efficient as possible. And let's see, for this intersection, its performance may be based on these two intersections. And for this intersection, it may be most related to these intersections. That is the spatial consideration. So let's come to the reinforcement learning first. The first is the single engine case. In single engine case, the state transition is only based on the action at this time step and the state observation at this time step. So the next state is only based on current state and current action of one engine. For multi-engine case, each engine will have their own observation. You can regard it as the local state. So I think there are two basic annotations. The first is that the local state is based on all the state observation at this time step and the actions at this time step from all engines. And other is that it is also a similar form as single engine. Each engine, the local transition, the state transition observed by each engine is only depend on their own action and state observation at the current time step. For this paper, the author proposed a multi-engine with spatial temporal Markov decision process. That is, the state observed at the next time step by this engine is based on the state observed at this time step from the neighbors of each engine as well as the engine itself and the actors from their neighbors. So, just like this picture, this engine's next state observation will depend on the state observation and action from these engines, or you can say the neighbors of this engine. That's the basic idea of this paper. And based on this assumption, that means the local transition are dependent of other engines given the neighboring engines. That is, if we consider the control policy of this engine, we do not bother to consider this non-neighbor engines. And the second is that the personal reward is based on neighbors. That is, the performance of this engine is based on their neighbors. So we can use to evaluate the performance of this engine, we should have access to the information from these neighbors. And instead of using the centralized critic and decentralized actors framework, this paper utilized the decentralized actor-critic framework. That is, each engine will be modeled based on an actor and critic framework, so that they do not share parameters. Each engine learn their own policy, have their own observation, make their own action. And the active critic framework is a classic reinforcement framework, and I do not want to spend much time in explaining this framework. Simply, the framework is that the critic is used to evaluate what the actor does, and the actor is used to produce action to interact with the environment. And this is the and each actor critic framework is modeled as an engine here. And for the actor and critic, they have their own observer and they have their own objective functions. This is the objective function for actor. This part is the policy evaluation. Basically, it is used to evaluate the policy that the actor obtain right now, the performance of the policy this actor obtained right now. And this part is for optimize the cumulative reward during one trajectory based on current policy. And this part is used to motivate, to promote the randomness of the action, because the policy is the policy, parameterized policy, and the action is basically a value sample from this policy. So this is an entropy. To make this entropy as large as possible means that we hope that the action is has more diversity instead of concentrated on one single value. And the second is the critic part. The critic is used to evaluate the performance of the actor. So this is basically basically it is as it is the same as the DQ learning objective function. That is, the cumulative reward is approximated by a neural network. And this is the advantage function, which is derived from the critic. So this is the connection between critic and actor. The output of the critic is used to help to optimize the policy of the actor. So this is the basic framework of this solution. And then we come to another highlight of this paper, that is the neural communication as stated by the authors. This is a very, I think it's a little bit complex. They use many function approximators to manipulate the features. Now we can come to see this structure. This is actually the forward process of the overall architecture. First, we can look this part. This part is the forward process of actors. That is, this part is used to produce actions by each engine, and this is the actor. We can see this is multiple actors because there are multiple actions. Each part is one one actor here. Now let's come to see this part. You can see that for each engine, its action is conditioned on a latent feature, and this feature is the key part of this neural communication, because how to produce this feature is related to the information from the neighbors of this engine. So let's see how to produce this latent feature. And this latent feature is based on the message from three parts. The first part is the message from the state observation of each engine. The state observation includes the observation of the neighbors, and observation of the engine itself. And they also use this is message produced. This is the message, and this is a function approximator or a learnable functions. That is, you can regard it as a neural network here, and the input is the state observation. That's the first part. The second part is the message from last belief of neighbor engines. It's very easy to understand because this time the latent feature at this time step is based on the latent feature at next time step. And the third is the message from policy of neighbor engines. That it is also modeled with function approximator, learnable neural network here. And in this way, the latent feature of this engine can be derived from the information from the neighbors. I suggest that this is the neighbors of this engine. So this is the forward process of an actor for engine I. And then for each engine, the evaluation of its current state is based on the action from neighbor engines and its old belief. And this is the state value approximator. In actor critic framework, this is used to evaluate the state of this engine. And that is the overall forward process of this architecture. And to take a step further, the belief can be modeled on multiple time steps. If you in this case, the belief at this time step only depends on the message from current timestamp, but you can elong this process in multiple timestamps. For example, at this timestamp, you can the message from this timestamp can depend on the last timestamp and the timestamp before a timestamp before the last timestamp. So this is a multiple timestamps consideration. In all, I think this is a little bit creative inside idea. There's some creative inside idea because they use spatial temporal reinforcement learning. Naturally, especially in transportation community, spatial temporal feature is used to recover the traffic data and to use to predict the traffic. And they use this nature to model a control framework. I think it is a good application, and all the message is parameterized to become learnable. Thus, it basically can generalize many up-to-date communication-based multi-engine reinforcement learning framework. But I'm not sure whether such a massive model is efficient given sparse reward signal, because I think that there are many parameters to learn in this framework, and once the reward signal is sparse, I think there are not enough information for the engines to learn to obtain a good policy. So that's my share of review, and thank you for watching, and let's see next paper.